Welcome to the introduction to waves. The wave phenomenon is actually just a mechanism by which energy is dispersed in a medium by causing the medium to oscillate relative to the point of the disturbance. The oscillation of the medium is actually a simple harmonic motion. Therefore, we will be seeing very similar types of notation and nomenclature relative to the wave motion that we had with simple harmonic motion. The way we characterize waves, their amplitude and frequency and wavelength, the way the energy is related to the amplitude, all of these characteristics share very common equations with simple harmonic motion. So, let's begin. First of all, wave characteristics. How do we define a wave? What are the symbols and the concepts associated with wave? Secondly, we'll have a unique equation to describe the wave motion in terms of its velocity, frequency, and wavelength, as well as we'll look at a couple of types of waves. As a matter of fact, in terms of types of waves, you can see a picture of them right here. The slinky example on the bottom left. The top one is referred to as a compression wave, in which the hand moves forward and backward along the length of the spring, creating zones of high compression and zones of low compression. The other type of wave is a transverse wave, shown by shaking the spring up and down and creating the typical transverse wave form that we're very familiar with. Wave characteristics are a number of things. One is the wavelength, given as the distance between repeating points, whether that be crest to crest, trough to trough, or any two repeating points on the wave. Of course, wavelength, being a length, is measured in meters. Okay, and a typical transverse wave picture that we're showing here is illustrative of the wavelength. If it were a compression wave, we would be looking at repeating points of the same density. For instance, where the slinky was compressed the most to the next time the slinky is compressed the most. So our typical picture of a wave is a transverse wave. It's easiest to see the things about that wave that we can characterize. The other thing you can see in this particular wave is the wave has an excursion above and below the center line, and we refer to that as the amplitude up, the amplitude down. And that's important because it does relate to the energy of the wave. You can see here the amplitude as expressed as capital A, and it would be in meters as well. It's the excursion above or below the rest or equilibrium line of the wave. So imagine a smooth, calm lake. So that becomes our 0 point, and then making a wave in that lake, so the wave is above that median by amount A and below that median by about A. That's our amplitude. The frequency of the wave is the number of oscillations that the wave makes up and down. Go up, come down, and go back to your original point. That's one oscillation. And if we count those number of oscillations in 1 second, that's what we call the frequency. So fundamentally, the unit is oscillations per second, but that is named as the Hertz unit in honor of Heinrich Hertz. So far, we have wavelength, frequency, and amplitude as characteristics of our wave. And then we have to remember that a wave travels with a certain speed through the medium that it is supported on. And so the fundamental equation in wave phenomenon is called the wave equation, where the speed of the wave is the frequency times the wavelength. Wavelength is in meters, frequency is in reciprocal seconds, so that combination of units, meters per second, is the wave speed of that wave as it travels through that medium. So here's an example of a wave in which we've measured the distance between the crests. Of course, that's the wavelength. We've measured the height of the wave. That's the amplitude. And we're told the frequency is 5 hertz because the time it takes for one oscillation is 0.2 seconds. And frequency is 1 over the period. So this wave represents a wave traveling at 0.7 meters per second as its velocity. So we've used the wave equation. We've used characteristics of the wave, amplitude, frequency, wavelength, period, and that's all the information we can get off of this wave at this particular time. Waves have some interesting characteristics in terms of their propagation. There's interference, superposition, reflection, refraction, dispersion, and diffraction. The interference means that waves can come together and create different amplitudes, but then they pass right through each other as they're traveling waves. You can see this happening. Also, characteristics of waves, and you can think of light or sound as maybe the simplest example. Waves reflect, law of reflection. The angle of incidence equals the angle of reflection. There's refraction. That's where light changes its direction as it goes through a medium of different optical density. Dispersion is where the energy of the wave is changed as a result of the medium. And diffraction is a phenomenon in which waves interfere with each other either constructively or destructively as a result of interaction with a object smaller than the wavelength of the wave. Those phenomena are studied more specifically in the area of optics in second semester of introductory physics. So what we want to take a look at is a rather interesting property of waves that we can utilize to make certain measurements, and that is the concept of resonance and standing waves. Resonance refers to a situation where energy is being imparted into the system that is oscillating at a favorable rate, at just the right frequency or just the right repetition, and it creates a condition where the amplitude of the wave grows very significantly, and we can calculate what those resonant frequencies are, and by examining either physically by visual means or by auditory means or other means the standing waves that are created as a result of this resonance condition. So in going through there, we'll define what nodes and antinodes mean, what resonant frequencies are, harmonic series, and that really completes the entire investigation of the concept of resonance. If you want to see a very dramatic example of resonance, I suggest you take a look at the Tacoma Narrows Bridge resonance. Just Google that, look that up, Tacoma Narrows Bridge. And there'll be video showing this brand new bridge which was built and then within a span of I think 30 to 40 days was basically ripped apart by unanticipated resonant oscillations of the bridge that destroyed it. So that's kind of a dramatic example of it. In the laboratory, we simply create resonance on strings with oscillators to demonstrate that. But resonance occurs when the driving frequency produces waves that are constructively interfere to produce a standing wave pattern. So as a wave travels up and down a string, one wave interferes with another one going the opposite direction. And if the energy feeding the waves onto the string by, say, an oscillator at one end is matched with the velocity of the wave and the oscillation, then you get the amplitude of the wave growing dramatically as a result of this specific condition of resonance. And we'll see how do we calculate that. Here I show three pictures of a string in which we have created three standing wave patterns on that string. So mentioned on the left end of the string we have an oscillator, and on the right end we're going to have a pulley with a weight. So we can place mass on over our pulley and change the tension in the string, and that will change the speed at which the waves go back and forth on this string. If we adjust the tension just so, we can create one of these standing wave patterns. The first one that we would create actually by placing the maximum amount of weight on the string is called the fundamental or the first harmonic. Okay, the fundamental or first harmonic is our top diagram. It possesses one antinode, and an antinode is where the wave is maximum, so the peak in the middle on this one, and contrast that with the second wave below that, which has two antinodes, and of course the third wave, which has three antinodes. So that's a characteristic of the standing waves. How many antinodes does the wave have in its standing wave pattern? The nice thing about waves on strings like this is we can actually see it. We can actually adjust the weight hanging over the side of the pulley and change the tension in the string and create a standing wave pattern with 1, 2, 3, 4, or how many antinodes we want to put on there. So those patterns that I illustrated on the previous slide are for a string which has two fixed ends. One end, the oscillator it's a fixed end. The other end is a pulley end. That's a fixed end. So the waves have to go to zero at a fixed end. So both ends of those are nodes where the amplitude goes to zero. The antinodes are where the amplitude is a maximum. And if we have something like a rod, or let's say a meter stick, and we hold it down on a table so one end is fixed but the other end is free, then the free end is free to oscillate up and down. It's actually an antinode, isn't it? Because if you think of the fixed end, you're holding a meter stick down on the table with one end where the amplitude has to go to zero because that's a fixed end. The other end is going to be free, so that's an open end. And so they have different boundary conditions. Open ends are antinodes, fixed ends are nodes. So we'll be using that terminology, fixed end or closed, and open or free. Okay? So here we see an example of waves on two fixed ends. Okay? We characterize a wave condition where the length of L is the string between the two fixed endpoints, not the length hanging over the side, okay? And the mass of the weight hanging over the side creates a tension in that string given by mg, capital MG. The wave speed is related to the tension in the string and the density of the string. First, linear density, that symbol is mu, the lowercase m in the Greek alphabet, and that means the mass per unit length of the string. Okay, so that's a constant. And so by suspending weight over this pulley we can change the tension of the string and we can create different patterns. Here we're seeing the third harmonic, okay, and the third harmonic has 3 antinodes. Okay, so that's the pattern we're seeing. If we added more weight over the pulley, we could set up the second harmonic, and more weight the first harmonic. Notice we have here for waves on string, we have a particular wave speed equation that says the speed of the wave on the string is the square root of the fraction tension over linear density. Okay, so tension is the newtons of force acting on the string, and linear density is the kilograms per meter linear density. How many kilograms is 1 meter of this string? So that's a formula which is only applicable to one-dimensional motion, waves on a string. So let's contrast that two fixed end motion that's exemplified by waves on a string with waves on a open-ended system, one end being fixed, the other end being open. As I mentioned, we could illustrate that with a meter stick on the edge of a table, holding one end down and letting the other end freely oscillate. And you can see kind of a representation of this if this beam is a length L long, and if it oscillates, the free end will be at a maximum amplitude, and the closed end or fixed end will be at 0 amplitude. So what we're showing in the picture there is the first harmonic, where the length L is supporting 1/4 of a wavelength. Okay, 1/4, because think of the wave starting at 0, goes to a max, comes back to 0, goes down to a negative max, and comes back to 0. So what we're representing here on this diagram is that L is supporting 1/4 of a wavelength. The next amplitude, the next resonant picture would be 3/4. Tried to represent that below with a quarter on the end and 2/4 back to the beam's beginning. So that's 3/4 of a wavelength on that picture. These resonance pictures, I think, will become clear once you move into the laboratory work on standing waves. There are some effects on wave speed and relationships that we need to take into consideration as we are calculating waves, particularly waves in air, but also waves in materials that are characterized by a bulk modulus. Temperature effects on waves are shown here for waves in air, that the wave speed in air changes according to the Celsius temperature. So the first equation is a precise equation, and then it can be approximated by the second equation. The wave speed is 331 meters per second plus 0.607 times the Celsius temperature. And we did a problem in one of our chapters on a rock falling from a cliff and striking the ground, and then the sound propagating back up to the observer at a speed of 340 meters per second. So that was a typical wave speed, around, say, 15 degrees Celsius, something like that. So this is where that number would have come from if we had the temperature and we plugged it in here and calculated 340. Other materials that are characterized by density and bulk modulus can be, the wave speed is affected by these two properties. Imagine waves traveling through solids, even water, okay? The bulk modulus is a measure of the medium's compressibility. Of course, the density is a measure of the medium's mass per unit volume. So waves travel very fast, say through steel or iron or solids, because of the density and bulk modulus. They travel relatively fast through water, and obviously because air is a rather thin medium, they don't travel as fast through air as they would through a more dense medium. I mentioned the resonance example of the Tacoma Narrows Bridge in 1940, which was collapsed as a result of oscillations that occurred on the bridge due to the wind. The bridge had been designed for winds up to 120 miles per hour, but a wind of 42 caused it to collapse, and the reason was that resonance occurred, setting up harmonic motion of the bridge and tearing it apart. So you can look that up online. Other examples of resonance you might be familiar with is the fact that on an AM radio, as you're adjusting the knobs or adjusting what you're actually adjusting, is a resonant frequency, which is given by the product of the resistance of the receiver and the capacitance. And by adjusting the resistance, you change the frequency at which the receiver receives, and you're looking for that specific frequency where it amplifies the incoming signal to your radio, to your antenna. Another example of resonance, kind of a mechanical example, is if you're playing on a swing, as say a person is on the swing and you're pushing them, and as you push them, they go back and forth, and there's this particular point in the arc of that swing where you actually jump in and push, and then let it swing back and come back and then push again. And that is a case in which each time you push, you're adding energy to the system at just the right point, such that the amplitude continues to grow and grow. Okay, and in that case, you're adding energy at each period in which there's a certain amount of time it takes for the oscillation to occur, out and back, and then you add energy again, and it goes out and back. And that's an example of resonance as well. So finally, we just want to mention something about the energies of a wave. The energy is proportional to the amplitude squared. And you can think of that, that's relatively important. If you think, say, of earthquakes, if you have a minor earthquake, a small amplitude oscillation doesn't have as much energy, but think of a larger amplitude oscillation in which the energy is being proportional to the amplitude squared, means that it have a significant amount of energy and a significant excursion from the equilibrium value. So energy is proportional to the amplitude squared for wave phenomenon.